Hello and welcome everyone to the interactive tutorial session. This is the fifth tutorial session or the problem solving session which we are having today. So today we are going to cover the syllabus of week 5 content, that is on microwave resonators, which includes series and parallel RLC resonators, transmission line resonators, and waveguide resonators. So basically the week 5 covers all the microwave resonators, and we are going to cover some numericals and sample problem solving based on these microwave resonators. So before going into the numericals, I'd like to brief what have been already covered in week 5, just briefing the major concepts. So to start with, we have a series and parallel RLC resonators. So let us look at what is the condition for resonance. Can anybody type in the chat or tell me what do you think? What is the what do you mean by resonance, or what is the condition for resonance? Yeah, so as rightly said Lakshmi Narayanan, it's XL is equal to XC, that is one of the conditions. So to elaborate it, so when the inductive reactance become equal to the capacitive reactance, the frequency at which it happens is the resonance. And more intuitively I can say that the electrical energy oscillates between this electric field of the capacitor and magnetic field of the inductor, so under the resonance condition. So to start with, if you look at a series RLC circuit or something, you have something like this. This is our series RLC, wherein you will be applying a voltage, and you might have looked at input impedance, and you have seen how the input impedance is being evaluated. So R plus j omega L minus j into 1 by omega C. So this had been modified as R plus j omega L into 1 minus omega naught square by omega square. So the major thing to notice here is omega naught is the resonant frequency, which can be written as 1 by root LC, and omega, here omega is the operating frequency, and the real part of this impedance. So if I look at this is a complex impedance having real and imaginary parts. So the real part of this impedance is R, and the imaginary part is this omega L into so and so. So let us look at modulus of Zn of omega. So if I take the modulus of this Zn input impedance versus omega, so you have a graph something like this, wherein you have the minimum input impedance which is equal to R, and that happens when this omega is equal to omega naught. So at resonant frequency you have the input impedance as the magnitude of input impedance is minimum and is equal to R. So that is nothing but your condition of resonance. And now look at the concept of Q factor. That is very important concept. So in case of a series RLC network, the unloaded Q factor. So let us try to understand what is unloaded and loaded Q factor. So probably any of you can type in or tell me what do you understand from the video lectures. What is the difference between unloaded Q factor and loaded Q factor? Yes. You can type in the chat. What do you understand about unloaded and loaded Q factor, or what is the difference between these? So to give you some clues, so when I say unloaded Q factor, so we have to understand that loaded Q factor means, so we are loading an external some circuitry. So there we are loading a circuit, so acting like a load. So it is a say we can say it's like a load resistance RL is being connected to a network. So if I can say the Q factor of the external circuit is QE, and Q factor of the unloaded circuit, that means when no load is connected, the Q factor of the circuit is Q naught, and QL I can write it as the Q factor of the circuit when this particular external circuit is being added like a load onto the circuit. So these three are related. So I can write 1 by QL is equal to 1 by QE plus 1 by Q naught. Okay. So this is the loaded Q factor and this is unloaded Q factor Q naught, and QE is the Q factor of the external circuit which is going to be added to this existing circuit. So this is the difference between the loaded and unloaded Q factor. So in case of a series RLC network, so the unloaded Q factor is given by omega naught L by R, or I can write it as 1 by omega naught RC. Okay. A similar kind of analysis was being done for parallel RLC also. If you remember, R, L and C, all the three components are connected in parallel to the voltage source, and then this input impedance have been evaluated. So in this case, I will directly write the final conclusions which we draw from this. So in this case, if you take the modulus of Zn, that means the magnitude of Zn, if you take the magnitude of Zn, so you get a graph like this. So Zn versus omega, and so at the resonance, that means when omega is equal to omega naught, you have maximum impedance which is equal to R. So this is the maximum impedance and that is equal to R. So this is the case of a parallel RLC network. So now in this parallel RLC network, what is unloaded Q factor? Unloaded Q factor is Q naught is equal to R by omega naught L or omega naught RC. So this is the Q factor, unloaded Q factor of a parallel RLC network. Now the loaded Q factor. So when I say loaded Q factor, you have an external load of RL connected to this network. So in that case, QL is equal to omega naught L by R plus RL. This is in case of a series RLC network, and for a parallel RLC. So this is for series RLC, and in case of a parallel RLC, this QL is R into RL divided by R plus RL. Why? Because this RL is coming in parallel with the existing resistance R. So parallel combination of that R into RL by R plus RL, that multiplied by omega naught into L. So this is the loaded Q factor of a parallel RLC network. Okay. So these concepts are very important while solving the numericals. You need to understand these terminologies and parameters. So let us look at, so this is the first topic of discussion in week 5, that is series and parallel RLC resonators. Second topic is transmission line resonators. So a transmission line of a certain length and a termination. Maybe it could be a short circuited termination or it can be an open circuited termination. So that can act like a resonator. So when it will act like a resonator and under what condition, that is being discussed in the video lectures. And we also discussed the Q factor of transmission line resonators also. Then the third topic is about waveguide resonators. To be more precise about the waveguide resonators, so all of you know that this is a kind of rectangular waveguide. Say, suppose if you have the front plate and also the back of the waveguide, front of the waveguide and the back of the waveguide, if both of these are being short circuited, and I can say this will be called like a cavity. So I can call this as a cavity resonator. So this is a rectangular cavity resonator. Similarly, suppose if this is a circular or cylindrical cavity, then we call it as a circular cavity resonator. So in rectangular cavity resonators, so why do we go for waveguide resonators? Because in high frequencies, in case of transmission line resonators, the Q factor is low. So we go for waveguide resonators at high frequencies. Now, so in this cavity resonators, we need to have the concept of resonant frequency. Resonant frequency is Fc is equal to C by 2 into root of m by a the whole square plus n by b the whole square plus p by d, L by d the whole square. So let me try to give you a clarity of these variables. You all know that c is speed of light and m, n and L. So these three are the index of the corresponding mode of the waveguide. Say if I can tell you T, E, M, N, L. TEMNL. So M, N and L indicates the number of halfway variations along X, Y and Z directions. So if I say this is rectangular waveguide, so this is X direction, this is Y direction and this along the axis, this is the Z direction. So this is the dimension A and this is the dimension B and this along the length, so the basically the length of the cavity is the dimension D. So the third dimension is length of the cavity. So say if you have a mode TE101, then M is equal to 1, N is equal to 0 and L is equal to 1. So these are the index of the corresponding mode frequency. Okay. So now with these in keeping in mind, let us move on to the problems. Okay, let us start with the first question. First problem is input impedance of a series RLC circuit operating at 20% above its resonant frequency is given by. So we have been asked about input impedance. So we need to actually find the input impedance, expression for input impedance, and the question is about a series RLC. So when the question is about series RLC, we have already derived in the video lectures. You have seen how the input impedance of a series RLC network is being derived. So as I mentioned in the beginning just now, R plus j omega L minus j into 1 by omega C. So you all know this is a series RLC network wherein you have R, L and C. So R plus j omega L minus j into 1 by omega C will be the impedance. So impedances in series, we are just adding it up. Okay. So now simplifying this, we get an expression R plus j omega L into 1 minus omega naught by omega naught square by omega square. Okay. So now omega naught is the resonant frequency and omega is the operating frequency. So here the question is about a network or the series RLC network operating at 20% above resonant frequency. Okay. When we say operating frequency omega is 20% above resonant frequency, that means omega naught. So how do we write omega? Omega is equal to, so 20% above means 120 by 100. So 120 by 100 will be 1.2 omega naught. Okay. So this is the how we write omega is equal to 1.2 times omega naught. Now substituting this, R plus j omega L into 1 minus, so omega naught by omega will be 1 by 1.2 the whole square. Okay. So now we have to also write here, this is we also have to substitute for this omega. So substituting that, you will get Zin is equal to R plus j L into omega. Basically the omega is 1.2 times omega naught. Omega naught into 1 minus 1 by 1.2 the whole square. Now R plus j L 1.2 into omega naught can be written as 1 by root LC. So L and root L will cancel. So you get it as R plus j root L by C, root L by C and this you have to solve 1.2 into 1 minus 1 by 1.2 the whole square. Okay, so final answer will be r plus j root L by C, r plus j root L by C, and this has to be solved. So once you solve this, you will get it as 11 by 30. Okay, so this will be the input impedance. I hope this is clear. Any doubts you can ask or type in the chat. Or we will move ahead to the next question. If there are no doubts, we will go to the next question. Okay, so let's see the next question. Series RLC resonator has an unloaded Q factor. So that means this is a series RLC and unloaded Q factor is 1000 and at a resonant frequency of, so you are given with a resonant frequency 200 megahertz. If the resistance is 40 ohms, then the value of inductor. So you have been asked for the value of inductor. So the question is about, question can be solved based on the knowledge of the equation of unloaded Q factor in case of a series RLC resonator. So Q naught is omega naught L by R, where omega naught can be written as 2 pi F naught into L by R. Okay, so if you know this formula, this is just a substitution. Hope you can try this out and tell me the answer. Can you all try that, please? Q naught is 1000 is equal to 2 pi. F naught is 200 megahertz. 200 into 10 power 6 into L by R. So L value we have to find out. R value we know that it is 40 ohms. So L can be found. Hope I can get an answer. Answer option A, B, C, D. What do you think? Okay, somebody is telling option. Okay, Dr. NM, Mary Sindhuja. Yeah, you are saying that option A, 1 by pi micro Henry. Can you please verify that once again? 1 by pi micro Henry. Okay, somebody else is saying 0.1 by pi microhenry. Please have a look at the units. Please have a look at the units. Maybe you can correct yourself. Please take a look at the units. Yeah, Lakshmi Narayanan, as you said it, he's saying that option B. So let's see. I hope so here L is 100 by pi micro Henry. Okay, or I can say 0.1 by pi milli Henry. Okay, so we have option D as the right answer. Okay, thank you all. Thank you for trying. So let's move on to the next question. Series RLC resonator has a resonance frequency of 500 megahertz. So let us note down, this is a series RLC. You have a resonant frequency of 500 megahertz and you have an unloaded Q factor of 1000. Okay, and given R is equal to 200 ohms, and when a load resistance RL is connected to the resonator, the loaded Q factor is 100. So that means to a series RLC, a load RL is connected and now the loaded Q factor, that means QL, is 100. Now the question is, what is the value of that RL which make this Q factor go to 100? Okay. So let us try to evaluate this. So as we have seen already, the question is about a series RLC. This is very important. When the question is about series RLC network, first thing to note is how do we write the expression for unloaded Q factor. So unloaded Q factor is omega naught L by R in case of a series RLC. Now how about loaded Q factor? So loaded Q factor, so to a series RLC you are adding a resistance or a load RL. So this becomes omega naught L divided by R plus RL. Okay, so this is the loaded Q factor of series RLC. Now take the ratio of this. Okay, so Q naught by QL. So if I take the ratio of this, what do I get? One by R divided by 1 by R plus RL. So Q naught by QL is equal to R plus RL by R, or I can say 1 plus RL by R. Okay. Now Q naught and QL is known to you. 1000 upon 100 is equal to 1 plus RL is unknown to you. R is 200. Now the answer will be 10 minus 1 9 is equal to RL by 200, or RL is equal to 1800 ohms. So this is the value of load resistor which is to be added to the series RLC resonator, such that this unloaded Q factor of 1000 became the loaded Q factor value of 100. Okay. So answer option C. Hope this is clear. If there are any doubts, please ask, or we'll move on to the next question. I hope these are very clear. So if at all any question, you can stop me and ask me. So let us go to the next question. So this is a true or false question. Magnitude of input impedance of a series RLC circuit attains its minimum value at the resonance frequency. So to answer this question, we should think about series RLC circuit and the magnitude of input impedance. That means you need to remember the plot of modulus of Zin in case of a series RLC network. So if you remember, I hope you remember, in case of series RLC network, it used to be like this. So mod Zin versus omega, it is a minimum at resonant frequency, and the value of that minimum impedance is equal to R. Okay. So the question is, this magnitude of input impedance becomes a minimum at resonance. Is it a true or false statement? Yes, it is a true statement. Okay. Now going to the fifth problem. A parallel RLC resonance circuit has an unloaded Q factor of 900 and R is equal to 240. So now you have a parallel RLC wherein the unloaded Q factor is 900, resistance value is 240, and when a load of 120 ohm is connected to the resonator, that means you are connecting a load resistance of 120 ohm that is in parallel with this R or parallel with the RLC circuit, the loaded Q factor is. So you are being asked to find what is the loaded Q factor. So first of all, you need to write the expression in case of a parallel RLC. What is unloaded Q factor? So unloaded Q factor is R by omega naught L. Now, in case of a parallel RLC, suppose a load is being added RL, then in that case the loaded Q factor is R into RL by R plus RL into omega naught L. So this is the loaded Q factor. So in this case, take the ratio Q naught by QL. So if I take the ratio Q naught by QL, what do I get? 1 divided by RL by R plus RL. Okay. Or I can write R plus RL divided by RL. Or I can write 1 plus R by RL. So here Q naught is known to you, 900. QL is to be found out, is equal to 1 plus R by RL. Can you all please try to find this? 1 plus R by RL, 240 by RL is 120. Can you all please find out the value of QL here and give me the answer for this question? Yes, answer is 300 or option B. Okay, I hope by now the things are clear. Okay, now let's look at a problem in air-filled cavity resonator. So we are going to discuss about a cavity resonator. So as I discussed a few minutes back, say we have a rectangular cavity, something like a rectangular cavity like this. Okay, so this dimension is called as A, this denoted as B, and the length of this cavity is D. So when we can call this as a cavity, when the ends of the waveguide is short circuited, we can call this as a cavity wherein the wave will try to oscillate in the space inside the waveguide. So this dimension A into B is given to you, and the dominant resonant mode frequency is also given to you. In case of a rectangular cavity resonator, the dominant mode is TE101. So this had been discussed in the video lectures, if you remember clearly. So this denoted like MNL. So here in the case of dominant mode, M is equal to 1, N is equal to 0 and L is equal to 1. Dominant mode is the one having the least cutoff frequency. So that frequency is known to you, that is the 6.25 gigahertz. So the resonant frequency, the expression for resonant frequency is C by 2 into root of M by A the whole square plus N by B the whole square plus L by D the whole square. So if you notice, when we had a discussion on waveguides, we had these two parameters m and n. Now another one more parameter is being added, which is a dimension along z direction. So if you imagine it like this, so A is along x direction, B is along y direction, and this length of the cavity is along z direction. Okay, the length of the cavity is along z direction. So that's why we have the third dimension, that is L by D. Okay, so let us look at solving this. So the question is to find the internal length of the cavity. That means you don't know what is D, but you know that dominant mode is 1, 0, 1. So let us simplify that. Fc is equal to C by 2 into root of m is equal to 1. So 1 by a the whole square plus n is 0. So this term does not exist. Now the third term is 1 by d the whole square. Okay. So the resonant frequency is 6.25 into 10 power 9. You know the value of C. In centimeters it is 3 into 10 power 10 by 2 into square root of 1 by 3 the whole square plus 1 by d the whole square. Can you try finding out the value of d? Can you try to find out the value of d, which is nothing but the length of this cavity? It's a clear, straightforward. Okay. Okay, so as okay, there was a question about why I took 3 into 10 power 10. You can always take 3 into 10 power 8 meter per second, because the dimensions, that is A. So this is dimension A and this is D. So all these are in centimeters. So that is the reason I have kept 10 power 10 here. In fact, if I am putting 3 into 10 power 8 meter per second, then I should make sure that 3 centimeter is also changed to 0.03. And the answer, whatever I get, will be in meters. And then later I have to convert it to centimeters, so that I will get the right option here. So because all the options, answers, everything is in centimeters, I have made this as 3 into 10 power 10. Okay, I hope it is clear. So as somebody said, Lakshmi Kanta, yeah, as you said, answer is D. D is 4 centimeter. Yes. So if all of you try, you will get the answer. D is equal to 4 centimeters. Okay. So if there are no doubts, I am no more doubts, then we'll move on to next question. So far I hope you remember I have gone through some questions on series RLC resonators, then few questions on parallel RLC resonance circuits, and also some discussions on unloaded and loaded Q factors. These are very important discussions. And one other topic was about the cavity, that is waveguide resonators, or we can call it as cavity resonator. So this was one question from this cavity resonator or rectangular cavity resonators. The other topic of discussion was on transmission line resonator. Say you have a section of a transmission line. So when I say a section of transmission line, it will have a particular characteristic impedance, and it will also have its properties like alpha, beta, so like attenuation constant and phase constant, such parameters. So once you know transmission line, a section of a transmission line of certain length, okay, whenever we say transmission line, a certain section of or certain length or section of transmission line, and sometimes we need to say also say that whether it is terminated, so whether it is terminated with a short circuit, whether it is terminated with an open circuit, or whether it is terminated to a matched line, and so on. So any transmission line having a particular length and a particular termination, we can use it as a resonator. So I will brief out the discussion which was there in the video lectures. Say you have a short circuited transmission line. So whenever I say short circuited transmission line, that means the load, that is ZL, is equal to 0. Okay, and with the length of the transmission line is taken as lambda by 2. So in such a transmission line, short circuited transmission line with length equal to lambda by 2, then the unloaded Q factor, so the unloaded Q factor of that network is pi by 2 times alpha into L. Okay, what is alpha? Attenuation constant. What is L? The length of the transmission line. Now take the case, take another case which has been discussed in the video lecture. Take a short circuited transmission line, again same short circuited transmission line with length is equal to lambda by 4. In that case, what is the unloaded Q factor? That is equal to pi by 4 times alpha into L. Okay, so this is the expression, final expression derived in case of these two. So once if you know this concept, we can go ahead solving this particular numerical. So let us look at this short circuited half wavelength. Okay, so two things are clear. It's a short circuited transmission line and half wavelength transmission line. That means length of the transmission line section is lambda by 2. Has its first resonance at, so its first resonance is at 200 megahertz. So let me write down F naught is equal to 200 megahertz, and then it is told that the attenuation constant of the line is, so please correct this, attenuation constant is pi by 500 Napier per meter. Okay, so alpha attenuation constant is pi by 500 Napier per meter, and velocity of propagation, that means Vp, velocity of wave propagation is, okay, here also please make please read this like this, so 2 into 10 power 8 meter per second. Okay, now what is asked? Unloaded Q factor of this resonator at first resonance. So how do we find the unloaded Q factor of a short circuited transmission line with L is equal to lambda by 2? So let us use the first equation. Q naught is equal to pi by 2 alpha into L. Now we can also write this in terms of, because we are given with Vp, We can also write in terms of, basically we need to simplify this equation in terms of beta, or in terms of Vp. So we all know beta is omega by Vp, okay, or also we can write beta is equal to 2 pi by lambda. Here uh, here I can write beta is equal to 2 pi by lambda, and this could be written like pi by lambda by 2. So beta can also be written like pi by the length of the transmission line. So that means beta is equal to pi by L. So this can be written like Q naught is equal to beta by 2 alpha. Now Vp is given in the question. Please note the velocity of wave propagation can be derived from this. So beta can be written as omega by Vp. So omega is 2 pi f naught. So 2 pi into f naught is 200 megahertz. So 200 into 10 power 6 by Vp. The velocity of wave propagation is 2 into 10 power 8. Notice that it is not equal to c. So it is 2 into 10 power 8 meter per second. So beta can be found from here, 10 power 8. So finally you will get it as 2 pi. Beta is 2 pi. So if you substitute it here, 2 pi by 2 into alpha is also known to you here, pi by 500. Pi by 500. So 2 and 2 gets cancelled, pi and pi gets cancelled. So the unloaded Q factor is equal to 500. So this is the final answer. So this question is from a transmission line resonator. So to calculate the unloaded Q of a transmission line resonator. So it is specified that it is a short circuited transmission line with length equal to lambda by 2. So the derivation had been discussed in the video lectures. It is clear. If you have any doubts, you can go back and look at the video lectures once again. So once you know those formulas, you can substitute and find out what is being asked in the numericals. Any doubts, please ask. Now the session is open for discussion. If you have any questions, you can ask. Okay, sixth question. Okay, I missed a question. Okay. Let me just. Okay. So the question is about. Okay, it's a true or false statement. Let us look at that. Open circuited half wavelength long section of a low loss transmission line behaves as a parallel RLC resonator. Okay, let us have a look at the question. So this question is from transmission line resonator. Okay, and the question is about a open circuited half wavelength long. So when I say open circuited, so you have a transmission line. If it was shorted, we would say like this, we will short. And this is not shorted, so this is an open circuited transmission line having a length is equal to lambda by 2. Okay, so the question is about the behavior of this particular transmission line, whether it behaves as a parallel RLC, whether it behaves as a series RLC. So that is the question. So we can find the behavior of parallel or series RLC based on the input impedance. So what will be the input impedance? If you know the input impedance, we can come to a conclusion about the behavior, whether it behaves as a parallel RLC or whether it behaves as a series RLC. So the easy way is, so if you know that ZL is infinity, that means open circuited load. So if the load is open circuit, then Zin, you know the formula for Zin, that will be J Z naught cot H gamma L. Okay. Now, so this circuit, if I say low loss, if I can assume that alpha is 0, completely 0, if it is very less loss, then what is the condition? We can say that beta L. So L is equal to lambda by 2. So beta L will be 2 pi by lambda into lambda by 2, which is pi. But now here it is alpha is not 0. We have very low value of alpha. Okay, very low value of alpha. So in that condition, you cannot directly take beta L, but we have to derive it. Once you derive it, you will be able to say whether this behaves as a parallel RLC or a series RLC. Now, the behavior of parallel RLC, if you remember, what was the behavior of parallel RLC? That means how do we get the graph of modulus of Zin? In case of parallel RLC, you used to get like something like this. That means at resonance, that is, say this is a graph between magnitude of input impedance versus omega. So at resonance, you get the maximum impedance, that is R. So if at all the resonance at resonance, if you have the maximum impedance or the maximum value of magnitude of impedance, then we can say that it is a parallel RLC or it is not. So there is a little bit of derivation involved in that. You have already come across that in the video lectures. I am not deriving it here right away, but you all know that yes, it is behaving like a parallel RLC. So this is a true statement. Similarly, you can also check the behavior of open circuited length with the transmission line with length L is equal to lambda by 4 also. So these are things which you can look at and understand, try to understand based on the what is being done.
Ma'am, could you please show the second problem slide?
Okay, second problem.
Thanks, ma'am. It's okay.
Okay. So any clarifications or doubts? Okay, whether the solutions for completed assignments will be posted. Yes, of course, the solutions for the weekly assignments will be posted in the subsequent weeks mostly very soon. I think the first week would have already been first or 1 or 2 weeks complete solution would have been already posted. But definitely yes, it will be posted if not posted. So if there are no